everyone, welcome to the first ever paper reading session from Represent Tech. Today we have Aniket Singh, who is a data scientist based out of Ohio, and Bishal Lamichhane, who is a PhD student at University of Reno. They are gonna present their two papers. And if you guys have any questions in the middle, then you guys can ask the questions. Let's get started. So as we begin, Aniket and Bisal, do you want to start with your intro? Aniket can go first.
Hello everyone, I'm Aniket. I'm a vision system engineer, or you can say an AI engineer at the moment at Altium Cells. And I tried to do some research papers on the side.
Hi everyone, my name is Bishal. I'm a second year PhD student at the University of Nevada, Reno, Math Stat department. My main research is graph machine learning and network models, but recently, due to this wave of AI and LLMs, I got interested in doing a couple of projects using large language models, and it's been fun so far.
All right, awesome. I know you guys have the whole presentation prepared up. So who wants to go first, Aniket or Bisal?
I think I'm gonna go first.
Okay, sounds good.
Okay, so how familiar are you guys with large language models? I'm pretty sure everyone knows about it, but everyone has used ChatGPT, and that's how everything started. But we use ChatGPT. Pretty much everyone uses it on a daily basis. But are we aware that they also provide us with the wrong answers, right? I mean, most people would say that, but they don't know if it's actually true or not, unless they actually are an expert in that subject and they see something and, oh, okay, this is wrong. But this happens way more than what we would think. And also because of this wave of large language models, we thought that we need to do something in this field and see if we can assess them, evaluate them, and try to come up with some insights. Next slide. Let me go over the outline. I'm sorry. So we are going to talk about both of our research. We will provide you guys with some introduction and motivation behind it. And also we will discuss the methodology for both of the research papers and the results. We will also discuss some of the future direction and suggestions. So the motivation of research, of course, the popularity is the first reason that we thought that we need to assess these models. Actually, Bishal, as he said, his field is network science. And I was actually also involved in some network science related research with him. And AI was my main field. Even at work, I do computer vision, but nothing with large language models. But it really interested me to see what we can do with this. And a lot of people have actually started to get into LLM research, and it is actually quite fun and interesting. And most likely this is the future with multiple applications. So it is very important that we evaluate and assess the capability of these models, and especially how well they would fit into an application point of view. We have already started to see some of the applications, especially with chat. I'm not talking about the chat GPT, but like customer care using GPT's API or some other models. I'm not sure if you guys have ever heard of this, but there are some news that got viral when these models provide you with some wrong information or something very very silly or something very opposite to what they should have been trained on, such as there was an incident of Chevy dealership where somebody managed to convince the large language model to provide the car for $1, I believe. So models should not do that, right? If you're technically, even if they are just an AI model, they're working for the company. They shouldn't be just giving out a car for $1, even if the Chevy dealership didn't agree to that. Things like this can happen, and it has happened with so many other companies too, that we may or may not have heard about. So it's very important that we learn about how well they would fit into these applications. It works well with ChatGPT for the most part, but so research on evaluating LLMs requires little to no resources, and if it does require something, maybe a little bit of API cost that you will pay, depending on how far you are trying to get into this. But training an LLM or even fine-tuning is a different story, because these will cost thousands and maybe could be 100,000s or even more. And so anyone who is here or who will see this video, LLM research is something that is that you can start with as your initial research experience, like especially if you don't have a lot of experience in research, this is something you can start with. Why I'm saying that is when you are talking about application-focused research, you don't have to know too much. You just need to know what you want, what your goal is. You need to make sure you define those things properly, and you get into it, and you learn as you are doing the research. So especially for new students or students who are just getting into research, LLM is very appropriate for them. So and both of these research are very application focused. We are not focusing on the theories behind it. We are not focusing on how these models were made or how these models were trained. We are focusing on how these models just fit into our application point of view. So our first paper, Beyond Human Bidders, this was a paper where we created generative agents. I will get into what generative agents are, where we created generative agents to make them play a simple English auction. We will discuss a little bit about why we chose a simple English auction, but we wanted to learn how well these models would perform in this auction scenario, and how well they would actually behave like a human when given personalities. Dr. Palardi is not here, but he's one of the economics professor at YSU, so he was the main author, and then Bishal, and then me. We can move into the next slide. So, of course, the first goal to mimic to learn how well LLMs can mimic human-like behavior. We will get into how we did that and explore how well the LLMs would perform in English auction. English auction is a very simple auction scenario. It's far less complicated than the other auction types, and that was one of the main reasons why we chose this, because it's not a mathematical model or a very it's a language model. We shouldn't treat it like a smart model that has multiple other models built into it. So that's why we tried to use something that's much simpler. And especially how well personalities would make differences in the behaviors of these models, because we assign them with a personality. Let's talk about generative agents, first of all. So what are generative agents? These are agents, I think in the Stanford paper, it was first time introduced, I believe. I hope I'm not wrong. And these agents you can assign them with characteristics, with name, with personality, and they would try to mimic human-like behaviors. And with LLMs, you can take this a lot further, because LLMs have a much better understanding of the way humans speak, the way humans write, the way humans try to understand things, because it has been trained on vast language and textual data. So it has learned from it, and especially models like GPT-4 and GPT 3.5 has learned it pretty well. At least when we started this research, there was nothing that could be compared to GPT-4 and GPT 3.5. Open source models are now starting to catch up, but in this research we did not talk anything about open source models. Okay, we can go to the next. So as I said, we only use GPT-4 and GPT 3.5, and there is a framework that we utilized called LangChain. It's a framework that allows you to create memories, and you can give them with personalities. You can provide architecture to create generative agents, and not just for generative agents, but you can do a lot more than that. But we use LangChain for that, and there are other models out there at the moment that are starting to gain some popularity, but when we started the research, LangChain was one of the best options. And generative agents with different personalities. So we had 5 different agents and auction agents and 1 auctioneer. All of them have had different personalities, kind of like also a different lifestyle that we gave to them. We also gave them with different names, some job, and some especially personality types, such as some of them were extrovert, some of them were very cautious, I should say. So we had 5 different personality completely. And when the English auction was for a French wine, because we wanted to have something that would not have such value that would increase in the future. We wanted something that they can just think like, okay, we can just drink it and finish it, so we don't have to worry about, okay, the price might increase in the future. So again, something simple that would not create too much complexity. And then prompt construction. So this is one of the crucial part of the study, which we will discuss further. We use 3 different prompts. We can move to the next slide, I believe. So we had 3 different prompting techniques that we use. Simple prompting, which is basically a very simple, the way we explain some things to LLM when you're using ChatGPT. You don't put too thought into it. As long as you explain your point, that's more of what simple prompting would be. And chain of thought is an extension of that, where you are not just giving a simple prompt, but also giving some layers to it and trying to promoting some stepwise cognition that would help LLMs make better decisions. At least that's the goal. And we will discuss how well these worked or didn't work. And then tree of thought, which is again extension of chain of thought. This can help us create a lot more complex agents because they have a lot more critical thinking built into the prompt. And the way the prompt is constructed, we want the model to come up with the most favorable actions, which would hopefully help the models perform better. And we would learn if these actually helped or not again. So the auction setup, as I mentioned, we had 5 different auction playing agents. We named them Sally, Bob, Alice, and Frank. We also assigned them with a private value and a budget. So private value would be something that they think the wine would be worth, and the budget is how much money they have to spend. To see how well they would do budgeting, and also if they go above their private value, and also to see if they would bid more than when you are playing an auction, you always have a private value, right? Like if if I don't know, like a Pokemon card on eBay. Let's say it's worth $100 at the moment, but you know it shouldn't be worth more than 500. You are not supposed to bid more than 500, right? If you think it's worth 500, you should not bid more than that. That's how you win an auction, or by getting it for as cheap as you possibly can get. Okay. So I tried to keep it short. So we can see the results here. Just with simple prompting, we can see how Sally has, with GPT-3 model, has bid above, I believe, up to $2,000. And the dashed red line is the private value of the agent. So the agent has gone really far from the value that we assigned to it. Same thing with Bob. We can see Alice did a bit better, but still not the best. Same thing with Frank. James even started with the higher value than it was privately assigned. GPT-4, you can see it's much better compared to 3.5. It's, even if it's not the best, we can see it's doing a lot better compared to GPT 3.5. Now let's see for chain of thought. We can see it has significantly improved compared to simple prompting. And now agents are still bidding a bit higher than what it should have bid for. And in case of GPT-4, it's almost, in most cases, it's good. It hasn't bid more than what it should bid. And tree of thought is where we see the most significant difference, and models are actually performing the best, except GPT 3.5 is not the best, but still with just prompting, we can see the difference in all of these agents. Of course, how complex, how well defined the model is helped. In case of GPT-4, it's doing much better with any prompting compared to GPT 3.5. So complexity of the model itself matters, but the prompting also matters a lot. And we did 10 iteration of this, and that's when we came up with this. So we can conclude that the prompting really makes an impact. So the key findings, of course, model is very crucial. The prompt choices are very crucial. We can see how well Tree of Thought did, and maybe there is some other prompting techniques that could perform better, or maybe not. I'm not sure. But since we tested with these three, and we can see Tree of Thought was the best one. GPT-4 agents, they did very well in all three scenarios compared to 3.5, again, because how well this model was made, how the model is much more complicated and complex compared to GPT 3.5. Let's not get into the theoretical side of it, but I believe it's multimodal. That's why it's much better. But again, it's not fully revealed. So there's a noticeable gap in the simpler prompts and older models. Older models here means the 3.5, and simpler prompt, of course, it's going upwards of $2,000. That's a huge gap compared to what the private value is. And this is the main thing, actually, I think. When we were doing experiment, we noticed how well these models were, especially with GPT-4, how well these models were acting as they were made to act, basically. Like, they were supposed to act like an extrovert, and they did act like an extrovert. If the model was supposed to act extra cautious, they were extra cautious, which was great, how well they were able to mimic just like humans would talk or play an auction or do basic conversation. We did some of the other iterations too, with where we were not doing auction, we were doing some interviews, and these models were actually acting like almost like a real human. especially in GPT-4 case. So yeah, move to the next one. So from now, Bishal will take over this paper.
Hello, can you hear me? Yeah, okay. So as Aniket concluded, the behavior these large language models, especially GPT 3.5 and GPT 4, they showed was really interesting. Especially, they were able to mimic what a human would say. Right? We gave them different personas using this generative agent framework. And then after that, we thought more about if they're able to mimic what a human would say, we wanted to go a step further and see how does the self-assessment or how confident they are while answering different tasks. So that would be a next step to see if they would resemble any cognitive phenomenon similar to human beings. So that was our next interest. It makes sense to do these kind of research because large language models, they are trained in vast corpus of human data. So they represent everything good and bad that we human have. So they represent our biases. In some way, they also represent our way of thinking. Right? So we wanted to see how far they go in terms of confidence, and that's what this paper is about. Okay? And our other co-authors, Suman, Devkota, and Chandra, they are not here, but we want to give a shout out to them. It was a really fun project working with them. Okay? So study of LLM self-assessments, tendencies via confidence score. So while these large language models are performing different tasks, we want to understand how confident they are while doing those tasks. So that's the main idea of this paper. And we focused on models like GPT, Bard, Claude, Llama models, which were at those times the popular ones, and I think still are ranked high in the Hugging Face ranking. Okay. And the key interest here is we want to see how these large language models, if they show any biases like the Dunning-Kruger effect. So the Dunning-Kruger effect, it studies how well confident or underconfident people perform or subject performs. So in this case, our subject would be large language models. And we want to see the alignment of self-assessed confidence with the actual correctness. Okay. And the significance of this is large language models, as Aniket mentioned earlier, are being used in real production cases. And in some cases like health sectors, law, the response these large language models give are really, they have to be really weighted properly to make sure they do not give anything wrong or anything biased. So understanding these behaviors of large language models will help us ultimately implementing them in applications. So the table one shows different variables that we use in our project. I mainly want to focus on these confidence scores. So we had 4 confidence score collected from these models. So they are namely absolute confidence and relative confidence. So absolute confidence is where we asked before answering the problem or before solving the task, we asked them how confident they are that they will be able to solve the problem. And we did that for relative confidence. We asked that, but with respect to other large language models. So we said, compared to other large language models, how confident you are that you'll be able to solve the upcoming task. So those are for the pre-confidence score, A1 and R1. And for A2 and R2, we did the same thing, but after giving them the problem, they solved the problem. And then we asked, now that you have solved the problem, how confident that you are you that you solved it properly? So those were the 4 scores that we used, and each correct represents whether the answer was correct or not. And we had different categories of problems and different problems level, which I'll talk about it briefly in next slide. Okay. So this was the chat interface example that we used to interact with GPT. So first we started by giving it a prompt. And again, we had to employ a mix of simple prompt and chain of thought prompt in this. We didn't have to use a tree of thought chain as we did in the auction paper. So here we would explain the model about what the process will be, and then the LLM will provide the AC of the first absolute confidence and relative confidence. That's prior to looking at the problem. And after the model provides the absolute confidence and relative confidence, we then go ahead and give it the problem to solve. And we wanted to get these confidence score before and after the problem is just to see how the confidence changes after the large language model has seen the problem versus how does it self-assess itself without looking at the problem. So there are some interesting results from before and after confidence score. And after the large language model provides the answer, and then it provides with the post problem AC and RC. Okay. And these were the test categories that we extracted the problems from, and these are the popular benchmarking data sets that's used to test these large language models. So we just extracted problems from these. And all of these problems were labeled from 1 to 5, where 1 being the easiest and 5 being the most difficult. And this was the simple prompt with explanation that we used for some of the models. So our main concern was that we wanted to make sure the method is consistent over all the different models that we are using. So for some models, it was just enough. So models like GPTs, it was enough just to give them simple prompt and they understood what the process of data collection was. But for other models, it was relatively difficult to make them understand, quote unquote, understand how the process is going to go. So in that case, we employed a chain of thought prompt. Okay. And between simple prompt and chain of thought prompt, all the large language models that we tested were able to understand what the task was, and they were able to give all the confidence score in the right way. Okay. So now let's see how did they perform in different confidence score. So we defined a new variable like these: high confidence correct, high confidence incorrect. So what this does is we count how many times the large language model was provided a high confidence score, and also after providing the score, the answer was also correct. Okay, so we want to see whether being confident always correlates to being correct. And as we see from here, it's not always true. And models like GPT-4, we can see for all the scores, A1, A2, R1, and R2, the count of the total number of problems where they were confident and correct was 25, and this is out of 40 problems. And you can see the total count of high confidence incorrect was also 15. Okay. So GPT 3.5 and especially GPT-4, it's always confident regardless of the correctness, and it was one of the interesting observations from this paper. And if we see other models like Claude Instant, we can see high confidence incorrect. So that means the confidence or self-assessment calibration in these models are not that good. Okay? So they were confident 21 times, but those 21 times they got answers incorrect. And then so this here, low confidence incorrect, it represents those models that have underestimation, right? So like GPT was always overconfident, overestimating itself. Then these models underestimate themselves. So Claude 2, we can see that when they were low confidence, here. So when low confidence and correct, we can see 2, and especially for Palm, we can see in 6 instances, they had low confidence, but yet their answer was correct. Okay. So these kind of behavior really unlock some interesting behavior that these large language models show while solving various tasks. Okay. So the key findings, as I mentioned earlier, was GPT-4 always showed a strong self-assessment. but also displayed overconfidence, where in the cases it was confident also got incorrect 15 times out of 40. Llama 13B exhibited a significant high confidence incorrect score, indicated a discrepancy between confidence and performance. And depending on the field, it might be very crucial for us to go dive deep into why this is happening. And Claude instance was overconfident incorrect answer. So high confidence incorrect of A2 at 21. Okay, and so A2 means absolute confidence after the model saw the problem. So similarly, from all this observation, our data does hint as cognitive bias like Dunning-Kruger effect, but it does not give us a certain answer whether we have a decay effect or not. Okay? It does hint us towards cases where high confidence relates to correct answer, but as we saw, there are instances where high confidence does not always correlate to correct answers. So to see a different side of this behavior, we define another variable called closeness. So the closeness would be if two scores are confidence scores, if the difference is less than or equals to 1, then we say those confidence scores are close to each other. And this one you can decide upon your applications if you want to change it to 2 or 3. It depends on how close you want your confidence calibration to be. And here we can see, so close correct means those are the instances where the confidence scores before and after solving the problem were close and they got correct. Okay? So a higher value in this category means that the model was consistently confident while also getting answers right. And one thing interesting was for A, so this is for absolute confidence and this is for relative confidence. The values for both of these are fairly similar. So it looks like between absolute confidence and relative confidence in this particular metric, there wasn't much different. But if we focus on particular models, then we can definitely see some very big differences in models like GPT versus models like Llama or Claude. Okay. And this one shows the distribution of confidence scores across different models that we tested. And we can see for GPT models, GPT-3 and GPT-4, the distribution is left tail. Right? So we can see most of the peak is happening towards the right-hand side. So as we go towards right, the confidence scores, the probability increases. So we can see different behavior for Claude versus GPT-4 here. And the GPT-4 always being confident regardless of the correctness. It can be seen here in the figure, like how concentrated they are towards the higher values of confidence score. Okay? So they are always confident regardless of the problem type, regardless of the category of the problem or correctness of the problems. So the main key insights that we got from this paper was problem level and test category highly influences the self-assessment of the models, but GPT models were always confident regardless of the accuracy and showing overconfidence in most cases. And again, so this behavior might be important for in some cases. For instance, if we are using models like GPT in applications where we generate creative things, for instance, text, or it's only like generating creative pictures where their underestimation or overconfidence does not play a big role. And in those cases, we are not really that concerned. But in cases or fields like health sectors, law, education, where even a slight overconfidence in these models might result a big problem in terms of applications. In those cases, we want to be very careful. So before applying these models, before using these models in daily applications, our research highlights that it's essential to understand behaviors from not only one perspective, but from multiple perspectives. So these observations, again, show the challenge of developing AI that is not only high performing, but also that contains an accurate understanding of its limitation. And that's where this idea of self-assessment and confidence comes. We want to see how models, if they had to score themselves, how they would do that. And this again, at end, connects to a need for ethical consideration and a safe AI deployment. And as a part of the future work, we want to see one of the things that we saw from this paper was in some categories, especially llama models, three other categories they did poorly, but in one specific category, their confidence score was more stable and they were more accurate. Okay. So this brings different next question on if we fine tune model into specific domain, how will the confidence change? Right? So, for instance, GPT is a general purpose, but if we take and fine tune, let's say, in a specific domain, and then give them tasks related to that domain, and also give them tasks related not to an entirely different domain, and then we can study how their confidence changes versus with the problem asked from that domain versus a different domain. And I think it'll be really interesting. And my I wouldn't say claim, but my guess is the confidence will be more for the fine-tuned domain. But this is yet to be explored from our side. And another future work would be to incorporate multimodal generative AI. What the research current literature has found is instead of giving just text, if we on top of text, if we give some supplementary visuals, then the model does relatively better in terms of prediction errors. So now to relate that to our research, we can test first by giving a textual question, and then also give them an image-based question and see how that additional layer of information helps change their confidence. And the third is employee feedback versus no feedback, and this is one of the current research we are doing. For now, in that research, we only focused on health domain, and where we are studying how providing feedback after each problem impacts in their self-assessment abilities. And so far from our results, we did not find any statistical correlation between feedback and no feedback. But again, that initial test had a small sample size of 100, which might not be very conclusive. So our goal is to increase that sample size to get enough power to detect whether there is a significant, statistically significant difference between feedback or not. And so another direction would be to use implicit probability values, which I'll talk a little bit more in next slide. And also these last 2 points I'll talk more in the next 2 slides. So when we are collecting confidence scores from large language model, we are explicitly asking them to provide how well they think they will solve the next problem. So besides that, there are what we call log probabilities that we can extract from these models through API calls. And this is from OpenAI's codebook. And so these log probabilities, which are different than the explicit confidence score that we ask from the model. So this allows us users to gauge the model's confidence in its output or explore alternative response the model consider. Okay. Now we want to see how this implicit log probabilities given by the model correlates with the explicit confidence scores that model provided us when it was solving the task. So that'll be our next future work to incorporate these theoretical probabilities into the mix. And the other thing is, this is very new. We haven't tried it yet, but I'm very excited to try this, what we call stealth assessment. So in all of the problems that we have discussed so far, both in the auction paper and this confidence-competence gap, the models knew they were being presented with the auction problem in the first paper. And in the second paper, the model knew they were being asked, the model knew that they were presented with these kind of problems, and they knew they were being asked confidence score. Okay, so I think when we do that, we are naturally giving a sense of biasness there, in a sense that the model knows what kind of tools to use. For instance, if we give a lead code problems to the lead code problem to solve, then the model knows it's a lead code problem, and then in that we are already giving a hint on how to solve the problem. Right? So this is where the stealth assessment comes. Is we for the model thinks it's doing one kind of problem solving, but under the hood we are studying a different behavior of the model. Okay? And one example would be again to connect with the lead code problems. So in lead code problems we have different hints that can be used. So for the model, we'll think it's only doing lead code challenges, right? And we give the model different hints. But to use the hint, model will have to buy or use its score to purchase the hints. So model will start with a base score that we will give to all the models, and if it gets answers right, the score will increase. But if it wants to purchase the hint, then they will have to buy the hint, and in there they could decide they would want to buy the hint, but now they have to think what's the probability that when I buy the hint I'll get the answer right. So but we won't tell the model that they are doing this task. The main goal will be just to see how well they do in lead code problems. But now we for these kind of problems, if we use linear programming or concepts from game theory, there is an optimal solution of how to use the hint and how to maximize your budget. And again, we won't be telling this to the model. The model only thinks it's doing lead code problem, but under the hood, we want to study how will these models optimize their score without explicitly knowing they have to do it. Yeah. And I think this, if model does this, and I think it's a step closer to generalizing knowledge in these large language models, where the model knows what to use without explicitly telling them. Yeah, I think that's all that we wanted to cover in terms of our research. So if you have any questions, we'd be more than happy to answer them now.
Hi, I had a question.
Mm-hmm.
So, you know how you guys said you're testing feedback on 100 samples right now, right?
Yeah.
Um, so if you were to increase the sample size,
Mm-hmm.
how would you determine the outlier? Like the
So,
unusable.
yeah, I see. So one thing with GPTs, outliers, as we saw, let me show you this graph. See this confidence. In this case, we do not really care about how accurately these models do. We only care about how accurately they assess their own confidence. And in models like GPT-4, they're always super confident. Their confidence score hover around 0.9. But as you mentioned, if we do some open source model, there are cases where they have outliers. In that case, we have to study individually to see whether that outlier was due to type of problem. For instance, let's say in all level 2 problems they did really good, but in one level 3 problems there was an outlier in the confidence score. So in this case, we will have to look at it individually and see what might be the reason behind it.
Thank you.
Yeah.
Thank you so much, Bishal and Aniket.